And welcome everyone to the second part of our 34th lecture. In this portion of the lecture we will be talking about two-dimensional curl. So curl of a vector field is a measure of the vector field's tendency to rotate counterclockwise at any given point. So where we see the vector field rotating in a counterclockwise manner, as here on the left, this is where curl is positive, and if it is rotating in a clockwise manner, that is a negative curl at the origin here. And in fact, we'll see that this vector field on the left has positive curl everywhere, in fact. So that's the intuition. The curl is a measure of the vector field's tendency to rotate counterclockwise. For the mathematical definition, if you have a vector field f hat given by component functions f and g, and it is a C1 vector field, again meaning that the component functions both have continuous first partials, then the curl of f hat is the partial of g with respect to x, so the second component function differentiated with respect to the first variable, minus the partial of f with respect to y, that is the first component function differentiated with respect to the second variable. And the order here matters because one of these gets a negative and the other does not. And we write curl symbolically as nabla hat cross f hat. So where divergence was a dot product of these two quote-unquote vectors, this one actually being a vector and this one being a quote-unquote vector, the curl is the cross product of the two. So this is another place where we can kind of see the relationship, the connection between dot product and cross product, the idea that these are two complementary operations. So a note on the notation here, as I said in part 1 of this lecture, curl is more properly defined for three-dimensional vector fields. This two-dimensional definition of curl is somewhat adapted for our purposes since we're working in 2 dimensions here. But in 3 dimensions, curl, the notational choice for curl makes a great deal more sense because nabla cross f is actually given by this cross product version of these two vectors. So we're going to take the I hat, j hat, k hat unit vectors. We're going to take the entries of nabla here, partial with respect to x, partial with respect to y, partial with respect to z, and then f hat, if f hat is fgh, that makes up the bottom row. And we take this determinant of a 3x3 matrix definition of curl, definition of the cross product rather, and that gives us the curl. So the notational choice for writing curl as a cross product makes better sense when you're dealing with a 3-dimensional vector field so that cross product is actually defined. Cross product is only defined for 3-dimensional vectors. And then you can see the logic of the choice. What we're actually seeing here is our definition is the k hat component of curl. So when I was if I were to work out this cross product, I would have k hat, I would have this bottom left submatrix, and its determinant would be the partial of g with respect to x minus the partial of f with respect to y, which is exactly what I'm getting here. So in some sense, curl is made up of an I hat component, a j hat component, and a k hat component in 3 dimensions. And they all represent rotation, and the vector that they're associated with is perpendicular to the plane of rotation. Rotations happen in a plane, right? If you've got a disk and it's spinning, it is a plane, and there's a plane in which that rotation is occurring. And it's the k hat component that represents rotation in the xy plane. And that is the portion that we're picking up when we only see the xy plane here, is the idea. So hopefully that makes some kind of sense. It's not necessary actually for our use of curl, but it is an attempt to flesh out the reasoning behind the notational choice for curl, and also get a glimpse of what curl looks like in higher dimensions. You're thinking about rotation in the YZ plane, rotation in this is pointing in the Y direction, so rotation in the XZ plane, and rotation in the XY plane. And it's only that last component of total rotation that we can see when our focus is limited to the XY plane here in 2 dimensions. So, the intuition again for curl, if I were to take a small paddle, like the kind of paddle that you paddle a canoe with or a kayak with, and if I were to drop that paddle down into my fluid, so my fluid again is a thin layer on the top of a horizontal surface, and my paddle, I'm going to drop it into that fluid with the handle of the paddle sticking straight up, is the movement of the fluid going to tend to rotate my paddle counterclockwise? If the way that the fluid is moving on the desk rotates my paddle counterclockwise at this point, then we are looking at a point with positive curl. If the movement of the fluid tends to rotate my paddle clockwise, then we're looking at a point with negative curl, I should say. So clockwise spinning means negative curl, as we've attempted to draw here. This paddle has a particularly fat handle, but that's fine. If the curl is 0 everywhere, then we call the vector field irrotational. So it is a vector field that does not induce rotation if it has 0 curl at every point. So incompressible or source-free was 0 divergence, and irrotational is 0 curl. We are going to have another word for irrotational vector fields, but we will put that off for just a moment. We'll discuss that presently. So let's do some examples and sample problems. Let's take this f hat, xy. This is our radial vector field that we've been discussing, and let's find its curl. So you can remind yourself what the picture of f hat looks like. You can guess what the curl might be for f hat, and if we compute it, we are taking the partial with respect to x of the second component function, which is just y, subtracting from that the partial with respect to y of the first component function, which is just x. Both of those partials are 0, so I get 0 curl. This is actually an irrotational vector field. If you remind yourself of what the vector field looks like, if I drop a paddle in here, this vector field just pushes the paddle away from the center. It doesn't spin it at all. It tends to just push it out, away. And it does not spin things. This is an irrotational vector field. We saw that this vector field had positive divergence and 0 curl. In some sense, it is the archetypal vector field for divergence. It's the archetypal divergent vector field and irrotational vector field. It is all divergence and no curl in some sense. So let's have a sample problem. Let's have you folks consider this vector field. We called this a rotational vector field when we were first discussing vector fields. Find for me the curl. You might want to sketch it, see if you can guess the curl ahead of time, but then actually find it using our formulas. And if you have done this, you will see that the curl of this vector field comes out to be 2. We're taking the partial with respect to x of x and subtracting off the partial with respect to y of negative y. 1 minus negative 1 gives me 2, and this vector field tends to rotate the paddle in a counterclockwise way. That's most evident at the origin, if you drop your paddle in at the origin, but even if I drop my paddle in over here at this point in the third quadrant, which I've indicated, rather the fourth quadrant, which I've indicated, I have these vectors on the outer edge of this paddle that are tending to push it in a counterclockwise way, whereas vectors closer to the origin might be tending to push it in a clockwise way, actually. But their magnitude is smaller than these vectors on the outside of the paddle, and so the vectors on the outside of the paddle win in the push-pull fight, and this paddle tends to rotate in a counterclockwise manner. We are seeing a positive curl of 2 everywhere for this vector field. Just as we said for divergent vector fields, these two, so this one first, let me say, this rotational vector field, it had positive curl and 0 divergence. It is the sort of opposite but symmetric example to the radial vector field we discussed previously. It's all curl, this one is all curl and no divergence. And as we said when we were discussing divergence, these are two examples where you have constant curl for both. One of them has curl 0, the other has curl 2 everywhere. That is not in general the case. So many vector fields will have non-constant curl. Curl will depend on your position in the xy plane, and curl can be positive in some places, 0 in others, and negative in still other points. So that absolutely happens. These two examples are nice because they are so simple and because they are so purely one or the other in some sense, but they are not the norm. Generally, things are messier. So when we talked about divergence of vector fields, we talked also about the divergence of conservative vector fields, and that led us to consider Laplace's operator. What about the divergence, or rather, what about the curl of conservative vector fields? So let's assume that f hat is conservative. That means it is the gradient of some little f, which is to say f hat is made up of little f's 2 partials. Oh, this should be the partial of little f with respect to y. That looks like a g there, so that's a typo. We're looking at the partial of little f with respect to x and the partial of little f with respect to y. The gradient of little f is what I mean to write here. It looks like maybe there's a y in there, but who knows, it's ugly. This should be the partial of little f with respect to y. So when we take the curl of that vector field, we're going to take the second component function, which is the partial of little f with respect to y, and we're going to take its partial with respect to x. From that, we will subtract the partial with respect to y of the first component function of f hat, which is the partial of little f with respect to x. So this is just the definition of curl here, together with the fact that big F hat is made up of these two first partials of little f. And these are the two mixed second order partials of little f, which are equal by Clairaut's theorem. And so their difference is actually going to give me 0. So because by Clairaut's theorem mixed second order partials are equal, we actually get a curl equal to 0 for conservative vector fields. In fact, checking this condition is how we check for conservative vector fields. And if I rearrange this slightly to write it as this difference being 0, that's exactly the statement that the curl of the vector field made up of little f and little g is 0. So what we've actually shown here is that if the vector field is conservative, then it has 0 curl. A bit more is true. In fact, if we allow our vector field to be defined everywhere, as we'll state formally on the next slide when we state this as a theorem, the idea of conservative vector fields is exactly the same idea as irrotational vector fields. Those are the same class of vector fields if you're only talking about vector fields which are defined everywhere. You have to be a little bit more careful if you start including denominators into your component function of your vector field so that there are points where it's not defined, or if you have logarithms or square roots involved or something so that there are points where the vector field is not defined, then you have to be a bit more careful with the statement of this theorem. But we will give it in this way, where we say if f hat is defined everywhere in the plane, then it is irrotational if and only if it is conservative. Those actually turn out to be the same idea. And this does make some sense. If you think about the kinds of natural phenomena that are modeled by conservative vector fields, as we said before, these are the types of phenomena where there exists some potential function that gives rise to the force field, which is to say they're the types of functions or the types of phenomena that have conservation laws. Things like conservation of energy, conservation of momentum, things of that nature. So for the types of physical phenomena where you do have conservation laws, things like gravity, where you can talk about gravitational potential, or movement due to the presence of static charges for charged particles, where you can talk about things like electrical potential. These forces tend to move things in straight radial lines to or from away from or towards the sources. So they don't make things start spinning in place. They're not going to make things spin, they're going to make things move in radial lines to and away from. They apply radial forces, both gravity and forces due to the presence of electrical static charges, move objects in straight lines in some sense. And when I talk about gravity, you may immediately rebel and say, well, no, the Earth rotates around the sun. That's true, but that's happening because the sun is applying a direct radial force on the Earth towards the sun itself. And that's not what is causing the Earth to spin around its axis. That's what's causing the Earth to spin around the sun. The Earth is always falling towards the sun. It's just doing so in such a way that it's continually missing and moving around. Much as Douglas Adams said, if you want to learn to fly, throw yourself at the ground and miss. The Earth is being thrown at the sun, but it is missing continuously, and so it's rotating around the sun. But it's only doing so because there is a direct radial force from this gravitational potential of the sun that is applying a force on the Earth towards the sun directly. Much like you can make a rock on a string spin around in circles by applying a continual force inward on the rock along your string. So, it's not making the Earth spin in place. The Earth is spinning in place, but that's because the matter that the Earth is made out of was already spinning when all that matter collapsed down to form the Earth. So it's an artifact of the fact that all matter was spinning shortly after the Big Bang. In general, forces or the types of physical phenomena where we have conservation laws, these are the types of physical phenomena where radial forces are being applied, and they don't generally cause objects to just start spinning in place. They instead cause objects to move towards or move away from the source of the force. Alright, so that is the idea for curl, where divergence is a measure of a vector field's tendency to expand or contract at a point. Curl is a measure of a vector field's tendency to rotate counterclockwise versus rotate clockwise at any given point. And today's lecture is going to be a little bit short, but we do have 2 lectures remaining, and we have plenty of time to jump in and talk about Green's theorem next time. We will state Green's theorem divergence form and Green's theorem curl form next time. We'll do some examples, and in our final lecture, we'll think about some of the implications and do some more examples and practice problems. I thank you, folks. I hope you have a lovely Friday.